Assalamu alaikum wa rahmatullahi wa barakatuh. Today we'll continue our lesson. Before we do that, if you remember last class, there was a concept, I gave a concept quiz. Okay, so did you solve the concept quiz? Let me share my screen to show the concept quiz. Okay, this is the concept quiz. Says determine the magnitude and direction and line of action of the vertical and horizontal components of hydrostatic force acting on the surface. Determine the resultant hydrostatic force acting on the surface. You remember we took this example, which is somewhat similar, except that now water is not above the surface, but it is below. Okay, so the water is now below. So how is the geometry? How is the calculation going to change now? Okay, so as we did in this one, you see, we try to isolate a volume of water that will be providing the hydrostatic pressure on the curved surface. In this case, it will not be from the top, but from below. Okay, so with this, okay, and then vertical, we have pressure distribution is trapezoidal. Okay, and the pressure force will be acting at the center of pressure. Horizontal, it will be uniform. The pressure distribution will be uniform. Okay, pressure distribution, and the pressure force here. Here, let me call it FH. This one, FV, the vertical one, will be acting at the centroid of this. Okay, and then you can, and the weight of the enclosed volume will be so here, which will be acting vertically downward. Okay, so pretty simple, straightforward. FV, the vertical component now, the pressure force be provided by the pressure of the centroid times the area. Okay, times the area, and the area of the curved surface we have 1 meter by 1 meter. Okay, 1 by 1. Okay, because from here to here, the radius, which is 1 meter. Okay, and then the normal to the page, you have 1 meter. Okay, so and then the horizontal pressure force will be equal to, here you have the pressure at the centroid, okay, times the area. Okay, the pressure at the centroid, E bar, is going to be gamma H, and H here is 1 plus 1 over 2. 1 plus 1 over 2 times the area. Okay, because from the top of the water surface, you have 1 meter, and then this is 1 meter, then half is 1 over 2. Okay, then vertical component is going to be FV minus W. What is W? The weight of the fluid enclosed. Okay, which is gamma times the volume. Okay, and what is the volume of the enclosed fluid here? It's going to be the area times the width. Okay, the area, if you complete this, this is quarter of a cycle. So pi r squared over 4, pi squared over 4, which is because it's a quarter of a cycle, should be 1 minus because for the volume, the area is going to be the cross-sectional area times the depth, the width normal to the page, okay, which is 1 meter, which is this shaded area. And this shaded area is going to be this total area minus the area of a quarter cycle, okay? So which is going to be 1 times 1, because this is 1 times 1, okay? 1 times 1 minus pi r squared over 4. This is the area times the width, which is also 1. This is W. Then once you have Fy, Fh is equal to Fx. Okay? Fx is equal to Fh because we don't have any other horizontal component of the force. So we can easily find the resultant of R, square root of Fy squared plus Fx squared. And then we can find the direction, theta, okay, tan inverse, okay, Fx, Fy over Fx, okay. So I hope it is clear. This is another simple case, which is somewhat similar to that, but not exactly the same. I'll just give you a hint. A semicircular tunnel is to be built under a lake, okay. The total hydrostatic force acting on the roof of the tunnel is to be determined. Just imagine a lake, you know, we build a tunnel under rocks. So imagine it's, and we want to pass through it, under it, okay? So this is the tunnel, and water will be acting on the surface, on the sides, okay? So to determine the hydrostatic force acting, as usual, we isolate the amount of water acting, okay? And this is Fx in both directions, and this is Fy, which is acting on the horizontal plane, okay? So Fy is straightforward, is pressure due from the height of the lake, okay, to this, okay, from the height, from the, you know, so the pressure due to the water will be used to calculate Fy here, okay, which is gamma H, which is the pressure times the area, okay, times the area, okay, the area of the funnel. Then Fx, Fy are equal, so they will cancel out, no need to even determine them. If we want to determine them, of course, it is pressure acting at the centroid times the area, okay, the area of this side, okay. But they're equal and opposite, so they will cancel out. And the weight of the fluid, the same weight here is the same weight here, okay. Same weight contained here is the same weight, so the weight is going to be 2 times gamma, 2 because you have W here and you have W here, another W, okay, times the volume, and what is the volume? Going to be the cross-sectional area times the width, okay. And how do we find the area of this portion, okay, the area of this portion? If we look at it all together, we can cancel these two, and then the area we will incorporate all the sides, okay. Cancel these two so that we have only gamma. So the cross-sectional area is going to be the area of this minus the area of a semicircle. So the area of a rectangle, the total rectangle, is the length times breadth, minus the area of a semicircle pi r square over 2, okay. Okay, when we move the area of the same cycle, this one, we will be left with these portions. Okay, then times the depth, times the width. Okay, times the width, let's say small w. And then from there we can get fr, since we can get fy, because fy is going to be fy here plus w. Okay, because w is acting vertically downward. Not to avoid confusion, we can use this fv, the vertical component. This we added the weight because it's acting downward, and the vertical force is acting down. In the previous case, we used minus, okay, because the vertical component is in opposite direction to the weight. If you remember, we said you can add or subtract the weight as the case may be. So please try to play around with some example, some exercises, okay, and understand exactly how it is done. Now let's move on to let's continue our buoyancy problems. Now we have started explaining what is buoyancy. That is the up thrust, the force acting vertically upward upon all bodies submerged, okay, either fully or partially in fluids. Okay, we explained the Archimedes principle. I didn't give you some history about the Archimedes principle. Okay, Archimedes is one of the famous scientists that lived, long time ago. And actually, what happened is the king at the time wanted to differentiate between his two crowns. One made of pure gold, and the other made up of gold, and then maybe silver and what have you. So he wants to know exactly which one is the original one. And then Archimedes, the scientist, one of the greatest scientists at the time, was thinking about how to go about it. Then he has a bathtub filled with water, just like your bathtub here, okay? And then he wants to take a shower, so he jumped into the bathtub. And he realized when he jumped into the bathtub, when he's inside the bathtub, the water spill, okay? Some water spill out. And that was when he realized, does that mean he displaces his own volume? Does that mean that when the body is immersed in water, it displaces its own volume, or it displaces an equal amount of liquid? It displaces its own volume in the fluid in which it floats. Then from that idea, he said, okay, in that case, because crown is an irregular shape, it's not something that you can easily, let's say, find the volume of a crown. So he said, okay, he can use this concept to find the volume of the crown. If he finds the volume of the crown, he can find the density, because density is mass over volume. If he finds the density of the crown, let's say it's equal to x. So if it's pure gold, then he knows the density of pure gold, density of gold. And if this is pure gold, if the density of the crown, by measuring the volume using the Archimedes principle, by immersing it in a liquid and measuring the volume of the liquid, and the volume of the liquid will be equal to the volume of the crown, then the non-density of gold should be equal to the density of the crown. If it's not pure gold, then the density will not be the same, okay, because density is constant. Density of water is constant, okay. Density of steel, density of silver, density of material largely remains constant, most especially solid. It is even gas, uh, uh, gas and liquid, that the density is so much affected, by temperature and other factors. For solid, the density virtually remains the same, okay, and that is how the principle was postulated, okay, Archimedes principle. Now, And then it provided the explanation as to why ships and boats float on water, despite the fact that the ship material or the boat's materials are either, sometimes they are steel, silver, they are made up of materials that ordinarily would sink in water. Although previously ships are usually made up with wood whose density is less than the density of water. Okay, but nowadays ships are made up of, let's say, you have steel, okay, steel whose density is greater than the density of water, yet it floats on water, and that is because of the buoyant force, okay, the upthrust exerted on the boat by the fluid, okay, and we are going to expatiate this further with this explanation, which we have started, okay. Now, I started analyzing this figure in the previous class, assuming this is a ship which is being loaded. Okay, initially when the load isn't that much, you realize that the weight here, as the weight increases, it sinks further. Okay, as the weight increases, it's submerged, it becomes completely immersed in water. When you increase the weight further, it sinks down. Okay, it sinks down to the bottom. Okay, now what happens in each of these cases? Let's take the first, okay? The first case, which is this one, okay? Here the buoyant force, FB, is equal to W, okay? And W is gamma times the volume, okay? Times simply mg, okay? We can simply use mg, okay? Then when you increase the load on the ship, it sinks further, because by increasing the load on the ship, the density of the ship increases, because density is mass over volume. The volume may slightly increase, or in some instances, because ships are usually hollow. Hollow means they're not like solid blocks. You have spaces inside filled with air. Okay, spaces filled with air. So often than not, the volume may remain the same, but the mass increases, so the density will increase. When the density increases, it will now be able to displace more water. Okay, and then you have case 2. In case 2, in that case, the volume of the liquid displaced increases, because the shaded portion indicates the volume of the ship submerged, which is equal to the volume of fluid displaced. So in the second case, also, the buoyant force is equal to the weight, because it is still floating, okay? But the buoyant force here in the first instance is less than the buoyant force in the second case, meaning the buoyant force in the second case is greater, okay? Because it is equal to the weight. When the weight increases, the buoyant force increases, okay? Now, let's move to the third case. In the third case, the ship is completely immersed in the water. So in this case, we have the maximum displacement of the fluid, okay, of the liquid, okay? This gives the maximum amount of liquid displaced. Hence, the buoyant force in this case is maximum. Okay, the buoyant force here, the buoyant force is maximum. Hence, in this case, you have the buoyant force being equal to the density of water, G, and the volume of the liquid displaced. Okay, because in this case, you have the maximum volume of the liquid displaced, and this maximum volume, even if it sinks down to the bottom, is the same thing, is the same volume. Hence, in the fourth case, here, the buoyant force in the third case is greater than the buoyant force in the second case. As indicated by the arrow, you can see it is a little bit bigger, but the arrow for the buoyant force, which is blue in 3 and 4, are the same, because the buoyant force will no longer increase. Okay, the buoyant force remains the same because of the fact that the volume displaced by the fluid remains the same. Density and G are virtually the same, remains constant. So the volume displaced in both cases remains the same. What about the volume displaced here? The volume displaced in one is less than the volume displaced the second case, which is less than the volume displaced in the third case. But the volume displaced in the third case is equal to the volume displaced in the fourth case. Okay, VD3 is equal to VD4. Okay, so under conditions 3 and 4, the buoyant force has reached its maximum value. If you remember, I made an analogy with the frictional force. When you start applying the force to move an object on a surface, okay, when you increase the force, applied force, the frictional force increases until it reaches a limiting value, a maximum static frictional force. Okay, so the same thing with the buoyant force. As you are loading the ship, the weight of the ship is increasing, the buoyant force is increasing until the ship becomes completely immersed in water. Once it is completely immersed, the buoyant force no longer increase or decrease. It remains the same, constant, acting on the body. Okay. So in this case, as we are going to see, in the first case, the density of the ship is less than the density of water. Okay. In the first case, the density of the ship, let me rho S, is less than the density of water. Because if it's less than, that's the only condition why it will float. Okay. Okay, because if it is heavier, then definitely it will sink. Okay. Imagine the analogy of the comparison of oil and water. When you put oil on water, if the density of oil is less than the density of water, the oil will not displace the water. Okay. Otherwise, if you have crude oil whose density is greater than the density of water, then it is going to settle at the bottom. It is going to displace water because it is heavier. Okay. In the second case also, the density has increased, but it is still less than the density of water. Okay. It is still less than the density of water. But in this case, rho S1, sorry, yeah, the density in the second case is greater than the density of the ship in the first case. When you increase more load, the density increases further up till when it will be immersed in the water. If it is immersed, completely immersed in the water, it means the density of the ship is equal to the density of water. When they are equal, okay, at this point they are equal, so it will be just, immersed in water. Now, in the fourth case, when the ship is further loaded, then the density will increase beyond the density of water and it will sink at the bottom. And in the fourth case, you have the density of be greater than the density of water. And that is why the ship sinks. It goes to the bottom, okay, of the ocean, bottom of the sea. Okay. Now, someone may ask, what about submarines? Because you have, I told you, one of the main reasons why ship floats, despite having been made up of steel and what have you, because they have hollow spaces. Okay, they have hollow spaces inside. You have a huge volume while the spaces are not filled. They are filled with air, and we know the density of air is very, very. Is way smaller than the density of water. So when you calculate the total density of the ship, it becomes less than the density of water. That is why it floats. Okay? And that is why the more a ship is loaded, the more the depth to which it will be submerged. Okay, like in the second case, because it is loaded, the weight here, W1 is less than W2. So the depth to which it's submerged or it is immersed in water increases. Okay, for submarines, what happens is that they have an entrance, a chamber in which they can either allow air inside or water. Okay, so it is such design that the density will be either just equal to the density of water, so that they float on the surface, not on the surface, they become just immersed in the water, like in the third case. Okay, so this is like the case of a submarine, when the density of the ship will be equal to the density of water. Okay, and the submarine may decide to sink further below the surface of the water, because submarines are usually warships. They are used during wars, so they like try to hide, so that the enemies at the other end will not see them coming, while they can send their missiles beneath the water surface. So they may decide to go deeper down. And how will they do that? By increasing density. How does it increase its density? By taking in more water. When it takes in more water, the density increases, and the submarine can go further down. How can it move up? It will come up to the to the top of the water surface by now allowing air. When it takes in air, the density reduces, and when the density reduces, it can now come up. Okay, so you can see some exposed surface of the submarine on the top of the water. Okay, it does that by reducing its density. How does the submarine reduce its density? By taking in air. Because when you take air, the density of air just about 1.2, the density of water 1,000. So the density of the submarine is going to reduce. When the density reduces, water will, like the buoyant force, will push it off. It will push it upward. Okay, so I hope all these explanations are clear enough. Okay, now still on the floating bodies. Okay, it follows from this discussion that a body immersed in a fluid remains at rest at any location in the fluid where its average density is equal to the density of the fluid. Okay, so it remains at rest in the fluid where its average density is equal to the density of the fluid. Like in this case, when it's rho is equal to rho F, the density of the body is equal to the density of the fluid. It remains suspended in the fluid and is neutrally buoyant. Okay. The second case, it sinks to the bottom when its average density is greater than the density of the fluid. Okay, this I explained in the previous diagram. Okay, like in this case. Okay, and it rises to the surface of the fluid and floats when the average density of the body is less than the density of the fluid, like in this case. Okay, and I demonstrated with the previous diagram as well by citing example with ship. Okay, now for a body floating on the surface of a liquid, the total weight of the body must obviously be less than that of the liquid it displaces. Okay, the total weight of the body is less than the weight of the liquid displaced. Okay, total weight of the body is less than the weight of the liquid displaced. Okay, because if you look at this, the weight of the liquid it displaces only this volume. This is the volume of liquid displaced, while the volume of the body is more than the volume of the liquid displaced. Okay, and that implies that the body is, although the volume is higher, but the density is less. Let me use, okay, density of the body, rho g, a volume. Okay, let's say water. Okay, now g is constant, cancel out. Okay, the volume of the body is greater than the volume of the displaced liquid, but then the density of the liquid of the body is less than the density of water. Okay, so when you multiply that out, you will realize that this statement holds true. Okay, that the total weight of the body must always be less than the weight of the liquid it displaces. It turns out that the portion of the body volume is submerged, but the remaining portion is positioned above the surface of the liquid. Okay, since the system is stationary, the two vertical forces must be equal. That is the weight acting, W, and the upthrust, which is the buoyant force. Okay, must be equal. Okay. So here the weight is equal to the upthrust. Okay, and the upthrust is rho F G V submerged. Okay, this is the volume, the submerged volume. Okay, so the submerged volume is equal to the weight over rho F G. So if you look at this formula, the buoyant force depends on the volume submerged. It depends, and the volume submerged is equal to the volume of the fluid displaced. Okay, so it depends on the volume of the fluid displaced. It's directly proportional. You can say FB is directly proportional to the volume of the fluid displaced. Meaning, as the volume of the fluid displaced increases, the buoyant force increases, and this is exactly what happens here. Okay, as the volume increases, the buoyant force increases up till when the volume reach a maximum value. When the volume of the fluid displaced reach a maximum value at the under case number 3, it reach a maximum value, the volume no longer increase, then that is when the buoyant force becomes maximum. Okay, and even when the ship sinks to the bottom, the buoyant force remains the same. Okay, the value of the buoyant force remains the same because of the fact that the value of the liquid displaced by the ship remains also the same. It does not increase any further. Okay. Now, buoyant force is proportional to the density of the fluid. Okay, and thus we might think that the buoyant force exerted by gases such as air is negligible. From this formula, okay, the buoyant force equal to rho FGV. Okay, so it's proportional to the, if the submerged volume remains constant, G is constant. Okay, so it increases with increase in the density of the fluid. Okay, it increases with increase in the fluid, in the density of the fluid. So gases possess usually negligible density. Okay, and we might think that the buoyant force exerted by gases such as air is negligible. Okay, because their densities, the density of gas is usually negligible compared to the density of liquid. Okay, this is certainly the case in general, but there are significant exceptions. For the volume of a person, for example, the volume of a person is about 0.1 meter cubed. Taking the density of air to be 1.2 kilogram per meter cubed, the buoyant force exerted by air to the person is now calculated to be 1.2, very small. If you compare to the weight of the person, person's weight in air is about 788. Okay, and the buoyant force exerted on the body, 1.2 Newton. So therefore, ignoring the buoyancy in this case results in an error in weight of just 0.15%, which is negligible. Okay, which is negligible. Whereas if it were to be in liquid, you remember the instance when we weigh an object to be 7 pounds in air, but in water it becomes 4 pounds. Okay, so the buoyant force constituted almost close to half, almost 45% of the weight. But this is so negligible that it can be neglected. Okay, so and the buoyancy effects in gases dominate some important natural phenomena. Okay, this is with respect to solid and gas. Okay, because humans are usually, although they have some, it's mainly made up of liquid. Human bodies are made up of about 70% liquid. Okay, but the density of liquid is way, way higher than the density of gases. But when you have gas and gas, then the buoyancy effect is dominating some important natural phenomena, such as the rise of warm air. Warm air has less density than cold air. So when you have warm air and cold air, the warm air, because the density is less than the density of cold air, it will rise, it will float over cold air. So that is why it will rise, okay, in a cooler environment. And that's the onset of natural convection currents. So that will now set in like convection current trying to cool the area, because when it rises, it may become cold. And then when it becomes cold, the one that is heated from the bottom will rise again. So it sets a convection current, movement of warm air, and then which is replaced by cold ones. And the rise of hot air or helium balloons and air movements in the atmosphere. This is like a hot air balloon. Okay, the altitude of a hot air balloon is controlled by the temperature difference between the air inside and the outside, and outside the balloon. Okay, since warm air is less dense than cold air, when balloon is neither rising or falling, the upward buoyant force exactly balances the downward weight. Okay, it exactly balances the downward weight. Now, the air temperature outside the balloon here, let's say, is 25 degrees Celsius. Inside, you are heating the air inside. So the air temperature inside, let's say, is around, let's say, 50 degrees, 25 and 50, meaning the air is very hot inside. And hot air, the density of hot air is less than the density of cold one. So the balloon will rise, okay? The up thrust will act. This, it will push it up, okay? It will push it up because of variation in density. The density of air here, it will be far, far less than the density of the air inside the balloon. So it will rise up, okay? If you want to, if you don't want to be rising up further again, you want to maintain the same altitude, then the temperature inside the balloon has to be made to be equal to the temperature outside, so that when the temperature is the same, then they will have the same density. You have the same density of air, just like in this case. If the density is the same, then it will be floating, okay? It will just, no, not float, it will remain suspended at the same altitude, okay? And this is the principle behind the hot air or helium balloon. Helium balloon, helium, the density of helium is less than the density of air. So in that case, it will automatically, move up. Okay, like it will go up. You know, even simple balloons that sometimes you can find in the malls uh, for kids, that is filled up with helium. Okay, is it helium or what is it? It is a gas whose density is less than the density of air. So that is why it is floating. When you release it, it will just go up. Okay, it will just go up. And that is because the density of air inside of the gas inside is less than the density of air. Okay, so that's why the buoyant force will now push it up. Okay, it is the buoyant force that is pushing it up, because if the density of the body is less than the density of the fluid, the buoyant force will push the object up. It will overcome it. Okay, it will push it up until it is exactly balanced by the buoyant force. Okay, until it is exactly balanced by the buoyant force. So a helium balloon, for example, rises as a result of the buoyancy effect until it reaches an altitude where the density of air, which decreases with altitude, equals density of helium in the balloon. Okay, hot air balloons work by similar principles. Now, the application of all this buoyancy effect is in hydrometer, which is a figure, an instrument used for measuring specific gravity of liquids. Specific gravity, that's relative density. Okay, relative density. Okay, this is the figure of the hydrometer. It is typically made up of a glass bulb that is uh, weighted on one side, so the hydrometer floats in an upright position. Okay, so you have lead weight here. You can see the lead weight. Yeah. Okay, so that it floats in an upright position. Okay, a stem of constant diameter is marked with a scale. This is the stem. Okay, and this is the scale. Okay, graduated scale for indication of specific gravity. Okay, by which is determined by the depth at which the hydrometer floats. Okay, you just put it in water or in the liquid in which you want to determine its relative density. And the hydrometer is calibrated such that in pure water it reads exactly 1. Okay, if this is pure water, so the calibration here or the value to reach exactly 1. That's because the specific gravity of water is 1. Okay, at the water-air interface, and the operating principle of the hydrometer is simply the buoyancy. Okay, in a heavier liquid, that is high gamma, when the specific weight is higher, the hydrometer will float more shallowly. In water, is 1 if it is 1. So if the density is higher, then it will push it up, isn't it? The buoyant force will push the hydrometer up. Okay, it is going to float more shallowly, and meaning the relative density is going to increase. Okay, the relative density is going to increase because the value increases downward. Okay, the value increases downward, so the hydrometer will float more shallowly because a lesser volume of the liquid must be displaced to balance the weight of the hydrometer. And in a light liquid, let's say petroleum, benzene, okay, hydrometer will float deeper. Okay, it will float deeper because relative density is less. Okay, so like it will be like to this level that when you have, let's say, benzene. Okay, because the relative density of benzene is less than that of water, so it will be less than 1. Whereas if you have, let's say, mercury, it will be lower, maybe somewhere to this level. Okay, if you have mercury, Hg, this, when you have fuel, let's say benzene. Okay, so the depth to which it sinks indicates the relative density or gives the relative density of the liquid. Okay, like I said, the main principle of the hydrometer is the buoyancy effect. Okay, is the buoyancy, that is the upward force exerted on bodies immersed in fluids. Now let's take some examples here. Here you have height of ice block below the water surface. Okay, you have an ice block in the figure here. Okay, which is submerged inside water to a depth of h, and 25 centimeter is above the water surface. Okay, so you have the weight acting and the upthrust. So consider a cubic ice block floating in seawater. Specific gravities of ice and seawater are 0.92 and 1.05 respectively. If a 25 centimeter high portion of the ice block extends above the surface of the water, determine the height of the ice block below the surface. Okay, we want to determine h, the height of the ice block below the surface, which is h in the figure. So now the height of the portion of a cubic ice block that extends above the water surface is measured, and we need to determine h. So here the buoyancy force in air is negligible. Okay, it will not become negligible if we are considering gases. Okay, because of the comparative values of their densities. Okay, the densities of gases are comparative. Okay, but that of liquid versus gas or solid versus gas, density is not comparative. The densities are not comparative at all. Okay, the densities in liquids and solids are way higher. Okay, making the density of air to be negligible. So this assumption is valid. The force, the buoyancy force in air is negligible, and the top surface of the block is parallel to the surface of the, and we have the specific gravities to be 0.92 and 0.025. Then the densities we just multiply by 1000. Okay, get the respective densities. So now let's analyze the weight. Okay, the weight of a body floating in a fluid is equal to the buoyant force. This we know. Okay, because of the equilibrium in the vertical position as shown in the figure. So the weight is simply equal to the buoyant force. Okay, and the buoyant force here is equal to the weight is equal to the density of the body times g times the total volume. While the buoyant force is equal to density times g times the volume of the fluid submerged or displaced. Okay, so g will cancel g, and then I have v submerged over v total is called density of the body over the density of the fluid. So the cross-sectional area of a cube is constant. Okay, this we know, and thus the volume ratio can be replaced by a height ratio. Okay, because the volume of a cube is simply the cross-sectional area times the length. Okay, so it's constant. So if we have the cross-sectional area times the depth. So the cross-sectional area in both cases, in this case of the volume submerged and the total volume is the same. The only thing that varies is the height. Okay, let me use h here. L squared. This is submerged. This is total height. Okay, so L will cancel L. Okay, so here we have only height submerged by the tube. Okay, over the total height. So the submerged height is h, and the total height is what? 8 plus 25 centimeter. We converted it into meters. Okay, and this is density of ice, which is the body, and the density of fluid, which is water, which is 920 and then 25. So from here we can make it the subject of the formula, which is 2.19 meters. Okay, you can imagine, this is the height submerged, 2.19 meters, while the height, that is floating on water that we can see is 0.25 meters. Okay, hence if you take, the volume ratio, okay, the density ratio, what is this? So approximately 90%, this is the volume ratio, okay, the volume of the submerged body. So this is 90%, meaning 90% of the volume remains underwater, okay, 90% submerged. Okay, for symmetrical ice blocks, to represent the fraction of height that remains underwater. It also applies to icebergs. Icebergs, are huge amount of, ice floating on water. But the vast majority of an iceberg is submerged. That is why we have the English, idiom that says tip of the iceberg. Meaning when you see an iceberg, you really substantial portion of it is lying below water. That is the literal meaning. But the technical, actual meaning is that when you have, let's say, a problem and it's called a tip of the iceberg, it means one may have a far bigger problem or whatever it is that is under discussion than what appears to be. I mean, the apparent presentation case may be way smaller than the actual manifestation of what the problem really is. Okay, that's why we say tip of the iceberg. Okay, and imagine just 10% is floating on the surface of the water, while 90% of the volume is immersed in water. Okay, and then again, we know the Dead Sea. In Jordan. In Jordan, we have the Dead Sea, which is sea water, but the salinity is the greatest in the world. The density of the water in the Dead Sea is about 24% higher than that of pure water. Okay, it has the highest salinity of all sea waters. Okay, so the density is way higher than that of pure water. Therefore, people float much more easily with more of their bodies above the water in the Dead Sea than in fresh water or in normal sea water. Okay? So in the Dead Sea, someone can just float because of the fact that the density of the body of the person is somehow just probably equal to the density of this sea water. If they are equal, it can just be partially immersed or completely immersed, or sometimes it's even less. Okay, the density of the person floating is less than the density of sea water. Okay, if it is less than, then you can just float without any effort. You can see this man, in this figure, just floating in the sea. Now let's take a 5 minutes break and look at this example. Okay. Okay, guys, let's move on. Oh. I told you have to remain till the end of the class. Okay, realize, okay, one person has left now. We're back. So now let's take this simple example to demonstrate application of the buoyant force, okay, on a metal part. Here you have a metal part as the second object, which is hanging by a thin cord, okay, thin cord from a floating wood block, okay, which is floating, okay, a floating wood block, object one, which is floating on the surface of the water. The wood block has a specific gravity, S1 0.3, so its density is less than the density of water, and these are the dimensions. And the metal part has a volume of 6,600 millimeter cubed. We have to find the mass M2 of the metal part and the tension T in the cord. Okay. So here a metal part is suspended from the floating block. Okay. And we have to find the mass and calculate the tension. So how do we set to achieve this? First, we have to draw the free body diagrams of the block and the metal part and apply the equations of equilibrium to the block to find the tension, and do the same thing to find the weight of the metal part. Okay, because when we find the weight, we can find the mass using W called mg. And this is exactly what we did here. For this one, we have the up thrust acting FB1 carry up, and the weight is acting downward plus the tension, all acting at the same point. Okay, because it is a wooden block and the cord is assumed to be at the center. Okay, so that's why here we have T plus W1. W1 is the weight of the block. Then for the metal part, of course, we will have also the tension going up. No tension is the force in rock is tensile force. It's a tensile force, which is when you cut through it, you show the arrow this way. Okay, you remember in statics. Okay, this is how we show tension. It is a tensile force. Okay, trying to stretch the cord. So this is T, the same T, because the tension is the same throughout the rope. So that's why here you have T. Okay, but here you have the buoyant force also acting. So T plus the buoyant force acting at the center also of the metal part. But then you have the weight of the metal part acting downward. So simple application of equilibrium here. For the first one, you can see that FB1 is equal to T plus W1. So the tension is FB1 minus W1. Okay. Then what is FB1? What is W1? Okay. The buoyant force is gamma D1, gamma VD1. Okay. VD1 is the submerged volume. The submerged volume is water, so the specific weight is this, and then we have we use the submerged volume. Okay, so we use not the total depth, which is 12.5, but we use 10. Okay, we use 10. And sorry, we use 10 minus 2.5. The submerged volume is now, instead of 50 by 50 by 10, we will now use 50 by 50 by 7.5. Okay, so that's why here we have 7.5. It's 10 minus 2.5 because we are to use the submerged volume. Okay, that gives the buoyant force. Okay, and so now we can put this, because this is millimeter cube. This is conversion from meter cube to from millimeter cube to meter cube. Okay, we have the buoyant force to be 0.184. Okay, the buoyant force to be 0.184. So how do we find W1? W1, we find it from the weight, okay, gamma S1 V1. Okay, gamma S1 V1. S is the specific gravity. Okay, in the problem we have the specific gravity as relative density to be S. Okay, and if you remember, relative density is the density of solid over density of water, which is gamma S, or body over gamma water. Okay. Okay. So now, if we want to find okay. So now, the specific, this is density. To find gamma S, which is the specific weight of the block, okay, is equal to the specific gravity times the unit weight of water, okay, times the unit weight of water. Okay, so that is why here, because the weight of the block W1 is equal to the specific weight of the block times its volume. Okay, so the specific weight of the block is equal to specific weight of water times relative density, which is obtained from this formula. Okay, so that's why here we are multiplying the specific weight of water times the relative density. Okay, from this. And then this is the volume. We use the complete volume because we are interested in finding the weight of the block, okay, the total weight of the block. Okay, so this is the weight of the block, and then the tension in the thread. Of course, we have FB1 and W1. So we subtract to get the tension, 0.11 Newton. Now we found the tension, then we can move to the second free body diagram. We know the tension, okay? We can find the buoyant force, and we can determine W2, okay? The buoyant force in the second case also is gamma V2, okay? V2 now in this case is the volume of the metal part, because the volume of the metal part is equal to the volume of the liquid displaced. Okay, volume of the metal part is equal to the volume of the displaced liquid. Okay, so that's why we're multiplying by its volume. And then from here, W2 is equal to T plus FB2. So W2 is found to be, we add this up, okay, we get W2. Okay, and then W equal mg. So to get the mass, we divide by gravity, and due to gravity, which is everything turns out to be 17.8 grams. Okay. So here it says, notice that the tension in the code is 0.1 Newton and is less than the weight of the metal part. The weight of the metal part is 0.18 Newton. Okay, this result is consistent with the common observation that an object will weigh less in water than in air. Okay, if it were to be in air, then the weight of the metal part and that of the tension has to be the same. Okay, the tension in the rope has to be exactly balanced by the weight it were to be in air. But because of the contribution of the buoyant force FB2, okay, which is helping in balancing the weight, okay, it is helping to balance the weight W2. So that's why the tension is less than the weight. Okay, so when solving problems that involve the buoyancy, draw an FBD, free body diagram, very important. Okay, and you know, we have been drawing free body diagrams for so many problems. So if you still have issues with, on how to draw free body diagram, I think you should quickly review, you know, chapter 3 of statics, where the free body diagram was introduced. Okay. Now, another simple example here says a rock weighs 1,000 in air and 609 Newton in water. Find its volume. Okay, want to find the volume. So simply, the force to hold rock in stationary water. I mean, this is the weight in air. Weight in air. And this is weight in water. Find its volume. Okay, so the volume definitely is going to be the difference, isn't it? Weight of water displaced, okay, which is the weight in air minus the weight in water, okay, which is simply 1,000 minus 609. 1,000 minus 609. So 1,000 minus 609. What do you have? 391 Newton. So this is the weight of liquid displaced, okay? And this weight of liquid displaced is equal to the weight of the body, okay? Is equal to the weight of the body. So simply, this is the weight of liquid displaced. This is the weight of the liquid displaced. So what is the volume of the liquid displaced? The volume of the displaced liquid, it will be the weight over gamma. Okay, it will be the weight over gamma, which is 391 over 9810, which is exactly what we have here. Okay, so this is the volume of the liquid displaced, which is equal to the volume of the body, okay, which is the volume of the rock, okay, because the rock displaces its own volume. Okay? The rock displaces its own volume. So simply, the weight in water plus upthrust is equal to the weight in air. Because the weight in air, when mass in water, it loses the weight, and the difference in the weight is equal to the upthrust. Okay, so this is a very simple case. Now, this is a problem in which you have a beaker, a tricky one. A beaker contains a layer of oil, which is the green, which is colored in green, and its density is ρ2, floating on water, which is the blue colored liquid, okay, which has density ρ3. A tube wood of density ρ1 and side length L is lowered so as not to disturb the layers of liquid, okay, until it floats peacefully between the layers as shown. So you can see the wood floating, you know, or at the oil water interface. So how do we find D, the depth of the top of the wood tube after it has come to rest, and the interface between so this is D that we want to find, okay? So here the magnitude of the buoyant force directed upward exactly equal the magnitude of the gravitational force directed downward, okay? The buoyant force depends on D, and the total buoyant force has two contributions from each of the two different fluids, okay? If you look at the water oil interface, the wood is floating, isn't it? Because only a portion of it is submerged. Okay, so in this case, look at the buoyant force acting from the liquid to be exactly balanced by the weight. When you look at the oil-water interface again, the wood is like inversely is floating in the oil, but upside down. Okay, not from the top, but from the bottom layer of the oil. Okay, so in this case as well, the buoyant force from the oil is exactly balanced by the weight of the wood. Okay, so now the buoyant force we know is balanced by the weight of the wood. Okay, this is what we know. Okay, the buoyant force is balanced by the weight of the wood. Okay, but the buoyant force is made up of two forces, FB2 and FB3. Okay, buoyant force acting on the wood due to water and one due to oil. Okay, so that's why we have FB2 plus FB3, all pushing upward because the direction of the buoyant force is always vertically up. It is always known. Okay, the direction of the buoyant force is always known. Just as the case of friction, the direction of friction is always known. It always opposes the relative motion or between two bodies, and it's always opposite to the direction of impending motion. When you have an object in which a force P is applied, the frictional force direction is always known. It's always opposite to the direction of impending motion. This is the direction of impending motion. So frictional force is always opposite to that. Same thing with the buoyant force. It's always vertically upward, not downward. Okay. So here you have FB, FB3 due to water, and here you have FB2 due to oil, all vertically up, and you have the weight of the block acting at the center. Okay, so the weight of the block W1 is equal to FB2 plus FB3. Simple. And then what is FB2 and FB3 in terms of the submerged volume? Okay, so the density times G, and DL2 for FB2 is the submerged volume. Okay, because it is said that we have a cube, isn't it? Bigger contains a cube wood. Okay, so it is a cube in which the length is L. Each length is L, so the cross-sectional area is L squared, and then times D, the depth to which the wood is submerged in the oil. Okay, so this one, for the depth to which it is submerged in the water, is going to be L minus D. Okay, so that's why here you have area L squared, the same area, depth to be L minus D. And then from here, this is FB2 plus FB, and then the weight of the wood is, the density ρ1 G and the volume L cubed. And then from here you can find D. Okay, so it's a very simple problem. Okay, but you need to understand the concept clearly. Now this is a concept quiz. This is a concept quiz which says to find the volume of the water displaced and position of center of buoyancy for a wood block of width 2.5 meter, 1.5 meter, and length 6 meter when it floats horizontally in water. Okay, the depth of wooden block is 650. Okay, so this is similar to one of the examples that we solved before. Okay, to find H. If you remember, we solved this one. Okay, we want to find H. Okay, so here we want to find the same H. Okay, okay, here is not H that we want to find, but we want to find the volume of water displaced. Okay, but the first thing we need to find is H, using the principle we used in finding H in that example that I have shown to you. Okay, so and then once we know H, then we can find the volume of water displaced by finding the volume of the submerged area. The volume of the submerged area, the volume of the submerged portion of the wooden block will be equal to the volume of liquid displaced. Okay, and here you have the buoyant force acting. This is the where it is acting, the center of the buoyant force, where it is acting through, and this is where the weight is for the wooden block. Okay? The two centers are different. B is the center where the point B is where the buoyancy is acting. Okay, the center of the buoyant force, and G is the center of gravity. Okay, as we are going to explain stability in a short while, we'll see the differences. Now, flotation and buoyancy, and here are also some other two exercises to just try your hands on, try to solve them. You have a wooden block whose size is provided and the specific gravity, which is floating in water. You have to find the weight of concrete of specific weight. This is the specific weight of concrete that may be placed on the wooden block, which will immerse the wooden block completely. Okay, which will immerse the wooden block completely. You have the wooden block, okay, which is floating in water. So find the weight of the concrete that may be placed, okay, on the block. So this is, you have the weight of the block, WB. So we want to find the weight of the concrete. When you add concrete on it, what is the weight of the concrete that can be added? Okay, which will mass the wooden block completely. So in this case, the buoyant force will be equal to the weight of the block plus the weight of the concrete. Okay, you can find the weight of the block because the volume is provided. Okay, the specific gravity, and then you can find the weight of liquid. Okay, and of course, when it is completely, the volume of the displaced liquid, it will be equal to the volume of the concrete. Okay, it will be equal to the volume of the concrete. Sorry, the volume of the wooden block will be equal to the volume of the wooden block. Okay, so try to find the volume of concrete that may be placed on the block that will immerse only the block completely in water, immerse the block and concrete together. Okay, so try to solve these problems to test your understanding of all the principles I just finished explaining here. Okay. Now, stability of immersed and floating objects or bodies. Okay, an important application of the buoyancy concept is the assessment of the stability of immersed and floating bodies with no external attachments. This topic is of great importance in the design of ships and submarines. You have a ship, it has to be stable, otherwise it may overturn or capsize, or it may sink. Okay, you have a submarine flowing, submerged, okay, completely submerged underwater. You have a buoy. The buoy here is used to direct ships or warn ships of some danger. Okay, it floats on top of water. Okay, so all this we need to understand how stable are they? What is their stability conditions? Okay, now first we'll discuss is stable equilibrium. Stable equilibrium, simply it is stable. The classic ball on the floor analogy to explain the fundamental concepts of of stability and instability. Instability is the opposite of stability. So in this figure, we will use 3 balls on the floor. Okay, case 1, which is stable. Okay, this is stable since any small disturbance here, someone can move the ball to the right or left, generates a restoring force due to gravity that returns it to its initial position. When you push the ball this side, it will come back, roll down because of gravity to the initial position. When you push it up this side, it will come back, okay, because of gravity. So at the end, it will be always stable, okay? It will always be stable, unless, of course, you push it off this, okay? So the stability has limit, okay? It is within certain limit, okay? That is, you don't push it off this edge. Okay, so this is a stable condition, okay? And a body is said to be in stable equilibrium if it returns back to its original position when given a small angular displacement. Pushing it, you are giving an angular displacement because the particles in the body are, are undergoing angular displacement, okay? And then you have neutrally stable equilibrium, okay? This is the case of neutrally stable equilibrium. Because if you move the ball to the right or left, it will stay put at its new location. When you push it this way, this is the new location, it will still stay here and be stable. If you push it to the left, it will change. The position changes, but it remains stable at the end, okay? So it has no tendency to move back to its original location. In the stable equilibrium, the body has tendency to move to its original location. In the neutrally stable equilibrium, the body has no tendency to move back to its original location, nor does it continue to move away. It remains in equilibrium, so it is neutrally stable. The body is said to be in a neutral equilibrium if it occupies a new position and remains at rest in this new position. So you see, it remains at rest in this new position. That is why it is in equilibrium when given a small angular displacement. Okay. Now the third one is the unstable equilibrium, which is case C. It's a situation in which the ball may be at rest at the moment. You can see here, the ball may settle, may be at rest, meaning in equilibrium at the moment. Any slight disturbance, any disturbance, even an infinitesimal one, however small it may be, if you give it slight angular displacement, okay, it causes the ball to roll off the hill, okay? It causes the ball to roll off the hill. It does not return to its original position. Rather, it diverges from it. Okay, this is unstable. And when it runs off the hill, we cannot predict exactly what. Of course, later it may still come to rest. But, it does gain its former position. Okay, it diverges from it. So this situation is unstable because when you give it small angular displacement, it becomes completely unstable. Okay, so this unstable equilibrium. Currently, it is stable, but given slightest, angular displacement, it will make it unstable. A body is said to be in unstable equilibrium if it does not return to its original position when given a small angular displacement. What about a case where the ball is on an inclined flow? When you have an inclined flow now, this is even not equilibrium because once you place it, it will not remain at rest completely. This one is originally at rest, but when you give it slight, infinitesimal angular disturbance, any disturbance, it will now make it to lose its stability. Okay, but this one is not even at rest from the beginning. Ab initio, it is not in equilibrium. So once you place it, it will definitely roll down the inclined plane. Okay, so it is not appropriate to discuss stability for this case since the ball is not in a state of equilibrium. In other words, it cannot be at rest and will roll down the hill even without any disturbance. Okay, you don't need any disturbance before it rolls down the hill. Gravity will definitely pull it downward. Okay. Now, let's apply this to the stability of immersed and floating bodies. Okay. The same concept of stable, neutral, and unstable equilibrium. For an immersed or floating body in static equilibrium, the weight and the buoyant force acting on the body balance each other, and such bodies are inherently stable in the vertical direction. Okay, such bodies are inherently stable in the vertical direction. Okay, when it is immersed, we are going to see all the figures. Okay, in the vertical direction. If an immersed neutrally buoyant body is raised or lowered to a different depth in an incompressible fluid, the body will remain in equilibrium at that location if it is neutrally buoyant. Okay? And when you immerse it, when you, raise it or lower it, it will still remain in equilibrium. But if a floating body is raised or lowered somewhat by a vertical force, okay, the body will return to its original position as soon as the external effect is removed. Similar to the stable equilibrium. When you push it, when you have a ball, you push it inside water, up thrust will push the ball up, still come above the water surface and float. Okay, so that is a stable equilibrium. Therefore, a floating body possesses vertical stability. Because when you apply vertical force to force it down, up thrust will push it up, and then it remains at equilibrium on the surface. While an immersed, neutrally buoyant body is neutrally stable, since it does not return to its original position after a disturbance. Okay? When it is completely immersed, okay, you can push it this way, a new location, or downward to a new location. So it doesn't return to its original location, but it remains in equilibrium. While if you have a ball, you push it downward inside, up thrust will push it up, and then it will come back to its original location. Okay, so a floating body has stable equilibrium in the vertical direction, while a neutrally buoyant body that is completely immersed, has a neutral equilibrium. A floating body possesses vertical stability, and then while an immersed neutrally buoyant body is neutrally stable because it does not return to its original position after a disturbance. The rotational stability of an immersed body depends on the relative locations of the center of gravity. Okay, we're talking about two things here. We vertical stability and rotational stability. Okay, this we are talking about vertical stability, like this one you can push it downward or push it down or up, vertical stability. This one also push it down or up. Okay, what about rotational stability of an immersed body? It depends on the relative locations of the center of gravity and the center of buoyancy, B, which is the centroid of the displaced volume. Center of buoyancy, B, is the centroid of the displaced volume. Okay. Now, stability of immersed bodies. So now we will treat the two cases separately. Initially, here we gave general description of the stability of immersed and floating bodies. Okay, now we will separate the two. We'll look at stability of immersed bodies, and then we look at the stability of floating bodies. Now, stability of immersed bodies. Okay, an immersed body is stable if the body is bottom heavy and thus the point is directly below point B. Here you have some weight. Yeah, okay, so it is bottom heavy. Therefore, with this weight, the center of gravity will not be at the centroid of this cycle or sphere, okay, but it will be something below, okay. So that's why you have the center of gravity below the center of buoyancy. While the center of buoyancy, as we mentioned here, the center of buoyancy is the centroid of the displaced volume, okay. The center of buoyancy is the centroid of the displaced volume. This sphere or spherical ball will displace liquid that is equal to its own volume, okay, and the center of buoyancy is the center of this displaced volume. So the center of buoyancy here will be just the center of the sphere, okay. But because of this weight that we have, the center of gravity will be lower than the center of the sphere, okay. So that's why we have G below B, okay, and this is a stable state. A rotational disturbance of the body in such cases produces a restoring moment to return the body to its original stable position, okay. So here, when you try to push it, okay, this way, it will return back to its original position because of the restoring moment, okay. restoring moment will bring it back to its original location, and that is because of the weight that you have here. Okay, and again, you can see that it is stable because these two forces FB and W are having the same line of action, so there is no net moment. You know, part of for stability, you have basically two equations. The vector sum of all forces must be 0, and the vector sum of moments must be equal to 0. Okay, okay. Are these two equations satisfied here? Okay, let's see. Sum of forces equals 0. Yeah, when you add all the forces acting on the body, must be equal to 0. Okay, and sum of moments equal to 0 because the forces acting, you have the buoyant force as well as the weight. Okay, and they have the same line of action, so there is no moment created. When you take moment at G and B, moment equals 0, because moment, you must have a perpendicular distance. If a force passes through a point, then its moment arm is 0, hence its moment value is also 0. Moment is the product of the force and the perpendicular distance. The distance has to be perpendicular. You must have perpendicular distance. If you have a point A and a force is through it, what is the moment of the force? The moment is 0. Because although the force has a given value, it has magnitude, but the perpendicular distance to the point is 0. Okay, so that is why here the total moment is 0. So when you try to tilt it, it will be brought back by restoring moment to its original position. Thus, a stable design for a submarine calls for the engines and the cabins for the crew to be located at the lower half in order to shift the weight to the bottom as much as possible. So for submarine, you try to make sure that the lower half will be this, is heavier, okay, such that the center of gravity will be lower than the center of buoyancy, okay, because that will make it to be in stable position, so that anytime if there is any angular rotational disturbance, there will be restoring moment that will automatically take it back to its original location. Okay. That's okay. Hot air or helium balloons, which can be viewed as being immersed in air, are also stable, since the heavy cage that carries the load is at the bottom. You know, for hot air balloon, you have the heavy cage that carries, then you have, you know, the balloon. Okay, so this carries most of the weight, and that is why it is stable. So it doesn't tilt. Okay, it, it, it doesn't move, let's say, upside down. It doesn't become, let's say, capsized in air at all. Because the center of gravity is lower. Okay, it's lower. And an immersed neutrally buoyant body is stable if the center of gravity G is directly below the center of buoyancy B of the body. So this is the condition, okay, for an immersed neutrally buoyant body. G must be less than below B. It must be below B, okay? The center of gravity must be directly below the center of buoyancy of the body, okay? And they must have the same line of action. They must not, what I mean by the same line of action, like when the buoyancy, center of buoyancy B is here, the center of gravity should not be here. Because if the center of gravity were to be here, then there will be moment created about B, because you have perpendicular distance. So this weight will have moment about B. Moment about B will not be equal to 0. And if it's not equal to 0, then it is going to rotate the object about that center, about that point. But if they are at the same, they have the same line of action, moment about B due to W is 0, because W, its line of action is passing through B. Moment about G due to FB is also 0, because the line of action of FB is passing through point G. So it will not have moment. Now, let's quickly take the quiz, okay? In our next class, we will continue from here. I will upload the quiz now on Blackboard, and when you there is time limit, 10 minutes to solve it, and then a clean picture of your solution and send it to my WhatsApp number, and just write your ID. When you send it, okay, just type your ID number. Just type it, okay? The quiz is starting now, okay?